great pleasure to introduce our next speaker, Brian Conrey. And in his course, he will talking about random matrix theory and statistics of families of L functions.
Thank you. So, yeah, I guess the goal of, well, a lot of analytic number theory, certainly of my research is to try to understand L functions as much as possible, the Riemann zeta function and all the L functions. We'd love to prove the Riemann hypothesis, of course, that's the main goal. We're very lucky as a subject to have such a great problem to attract people to be interested in it. And I think no one would disagree that it's the best problem out there, right? Felipe, you wouldn't disagree, would you? Okay. And that, as well as a number of other things, have really led to, I think, the blossoming of analytic number theory in recent years. Certainly the connections with random matrix theory have gone a great ways towards really broadening the field and helping our understanding of things. And if you look back over time, in the early 80s when Ivanets and some of his coworkers were introducing modular forms and automorphic forms into the subject, and that's become a staple now. And lots of other things have happened. So now we need to know, as analytic number theorists, we need to know everything, basically. So there's no getting around it. You have to know, you have to know your elementary number theory. You have to know algebraic and analytic number theory. You need to know representation theory, random matrix theory, mathematical physics, probability. Now you need to know differential geometry, as I found out yesterday. Differential, yeah, can you hear me? Is it okay? Yeah. So, but it's a good excuse, right? It's good to learn new things and to be forced to learn new things. So I'm going to be focusing on L functions and random matrix theory and sort of where that has all developed over the years. And I'm looking from the perspective of back when I was a graduate student. There was no conjecture for moments of the zeta function, for example. So we've heard about that a little bit as this week's gone on. And not only was there no conjecture known in general for the 2kth moment of the zeta function, the integral of zeta half plus it, an absolute value to the 2k, from 0 to t. We had some ideas about it, but I think really that we probably thought that there was no hope even of getting an answer to that. It just seemed way too complicated. But now we understand, after the work of Keating and Snaith, and then further work that really develops this to a very large extent, to a very precise extent, that agrees completely with all theory and with all numerics. It's all numerically testable now. We have a really good picture of sort of how L functions in families, how the Riemann zeta function and T aspect work for the statistics that at least give you moments, but also for the statistics, the local statistics of zeros and things like that. We can say very precisely how these things behave. Most of it we can't prove, but we're pretty confident that it's all correct, and it works in sort of great generality across basically anything that's sort of a family of L functions. And so we have this great connection with random matrix theory giving these models and sort of instructing us along the way. I mean, it turns out the combinatorics of these things are really complicated, and you absolutely need random matrix theory, if nothing else, but as a language to be able to describe a lot of these results. So, Zania, where's Philip? I'm going to talk about the LMFDB specifically for him, and he's not here. You need to go find him. No? You refuse? Okay. Right, okay, so I wanted to begin actually with talking about this Oh, here he comes. Good timing. I just asked where you were. Yeah. Right. So I wanted to begin by telling you about this great database of L functions where you can find absolutely anything you're looking for and see things kind of organized in a great way. And is really kind of at the beginnings of a long-term, infinitely long project to chart all L functions and the objects that they come from. So sort of a massive project. I mean, you can think of it like the, whatever your favorite math tables are, going back to the old CRC handbook and the Bateman manuscript projects, Gradstein and Rizhik, all that kind of stuff. But this is for L functions. And it's kind of vast and complicated but really pretty amazing. And I just want to go through a couple things on here to show you some of the stuff that's here. Oh, I should ask, so how many people have looked at the LMFDB before? Raise your hand. Okay, so maybe a third or so. So hopefully the rest of you will look at this and like it. Well, I should say, so Dave Roberts and Gonzalo Tenario are two people that are very involved in this project and have contributed a lot to it. There are about 50 people or more that have been involved in composing this thing. And well, from my perspective, it's about L functions, it kind of at the center of it. The LMFDB stands for L functions and modular forms database, LMFDB. And from my perspective, L functions are at the center, but you want anything that can lead to an L function to be charted as well. So you need the modular forms, you need Hecke characters, Dirichlet characters, you need elliptic curves and other varieties, you need Moss forms. You need anything that can lead to an L function should also be kind of a companion. So it doesn't quite all fit on here. Well, okay, so let's see if I can do this. Right. So you have this nice, pretty page, and there's all kinds of stuff in here. Maybe I'll just browse a little bit around, let's say, starting with L functions. Now, so L functions of degree 1. Maybe before I start, I should say sort of what the kind of an analytic framework for L functions from what we call the sort of the Cellburg class. There's sort of, when you sort of have the Cellburg class on kind of on the one side, on the analytic side, and then you have sort of Langland's classification on the automorphic form side. But let me just start with the Cellburg class. So let's say you have a Dirichlet series, n over n to the s, and it's absolutely convergent for sigma bigger than 1. And it satisfies 4 axioms, analyticity, that s minus 1 to the m, f of s is entire of order 1, or a finite order functional equation. So this should have a functional equation. And so there should exist parameters q bigger than 0, lambda i's bigger than 0, mu i's that are complex, but with the real part of mu I greater than or equal to 0, and epsilon complex, number of absolute value 1, such that if you form phi of s is q to the s product gamma lambda I s plus mu I, let's say I goes from 1 to r, times f of s, then this has a functional equation, phi of s equals epsilon phi of 1 minus s bar bar. And it's not unique because the gamma has a duplication formula. So you can split gammas up into, gamma of s over 2s. And so one of the points here is that the degree of f is twice the sum of the lambda i's. Okay, so that's invariant under however you write the functional equation. And so, I just did that. There's a couple more axioms. I'll say them in a second. But so when we look at degrees, then degree 1 would be like the Riemann zeta function, where you have a gamma of s over 2. You have lambda 1 is a half, and 2 times a half is 1. And so the Riemann zeta function has degree 1, as do all the Dirichlet L functions. Let's see if this works. So if we click on degree 1, then we see here some information, Dirichlet characters, functional equation, primitive characters. Now, there's a nice feature here that I just want to point out to you. So you see that some of these things have little dots under them, like degree 1, functional equation, Dirichlet characters, all that. Riemann zeta function doesn't. So that's a link, whereas these things are called nulls. And if you click on them, it'll tell you what they are. So if I click on parity, for example, well, okay. Then if I click on it, then the page splits apart like that, and it tells you what that is. A character is odd or even if it's odd or even function. And then you click again, and it disappears. Okay, if we click on, let's say, the order of a character. Smallest positive integers such that chi to the n is a trivial character. Well, okay. Anyway, so these nulls are everywhere throughout the website. And here, there's a little table of dots. And you can actually click on these dots, and it will take you to the page of the Dirichlet L function associated here. So, so this dot right here, that's the Riemann zeta function. Let's see, this thing is arranged as the conductor is along here. Okay, so conductor 1, you just have the trivial character that's 1 all the time, and that's the Riemann zeta function, right? And there is no, these are only primitive Dirichlet characters. There is no primitive Dirichlet character mod 2. The only character mod 2 is the one that's 1 on odds and 0 on evens, but that's just the same as a trivial character, but multiplied by something to get rid of evens. So the next one is 3. And it's yellow means it's an odd, and blue means even. And so you see all the characters here, and if you click on one of them, so like if I click on this dot right here, then I come to the page of the Dirichlet L function for the character mod 3. So every L function has its own page. And they all look kind of like this. You see the Dirichlet series, a functional equation, Euler product. The first few zeros are here. Some special values. If you scroll down a little bit, there's the z function. So every one of these things that has a functional equation, the functional equation means that you can multiply the function by some simple gamma factors that make it in order to make it real on the half line, it has the same absolute value as the z function has the same absolute value as the L function. Okay? But it's real and has sign changes at odd zeros, right? And so that's what so here you can see the zeros of the thing. And you can see sort of how big it gets. And this is for the Dirichlet L function of modulus 3. Some other things up here. You see some properties related, and then some links. If you want the the z functions, the L functions are calculated using Mike Rubinstein's LCalc program, and you can download the LCalc file if you want to do your own experimentation. You could go off to Dirichlet character and see its homepage. Okay. Well, let's look at what should we do now? Let's look at degree 2. Now, okay, so we do know that degree 1 L functions are either the Riemann zeta function or Dirichlet L functions, and then that's all there is. In degree 2, we think we know what all the degree 2 L functions are, but we cannot actually prove that yet. So in this Cellburg class, maybe I should finish the definition of that. So we have analyticity, functional equation, sort of a Ramanujan bound is that an is less and less than epsilon into the epsilon. So for every epsilon greater than 0, and then you have the Euler product, which is stated in a slightly unusual way that the log, so the a1 is 1, and the log of f of s is summation bn over n to the s, where bn is 0 if n is not a prime power. And the final thing is that there exists a number theta smaller than a half such that bn is smaller than n to the theta. This condition seems a little strange, but it actually rules out sort of counterexamples to the conjectures that you might naturally make about this. So one of the things, so this is the Cellburg class, and one of the things that Cellburg conjectures is that everything in this class satisfies the Riemann hypothesis, right? So all right, for anything, yeah. So f in the Cellburg class, S, f in S implies RH for f. In other words, all the non-trivial zeros of f are on the half line. Okay, and if you didn't have this condition, as well as some other conditions like the real part of the muse being non-negative, you can construct sort of counterexamples. So another conjecture is that the degree is an integer. Okay, so we don't actually know that that's correct. I mean, even though we call it the degree. We do know that there's nothing of degree smaller than 1. Degree 1 is only Riemann zeta function and Dirichlet L functions for primitive Dirichlet characters. There's nothing between degree 1 and 2. That's due to Kaczorowski and Pirelli. And then the subject has gotten to the point where people are trying to classify degree 2 things now. We'd like to say that degree 2 things are related to Cuss forms, either holomorphic Cuss forms or else Moss forms, and that's the only place that degree 2 things come from. Sort of the conductor or the level so QF, this is another invariant is equal to, it's not the same as the big Q there, but it's, well, okay, so it's 2 pi to the df times q squared times, it's kind of funny looking, lambda I to the, it's called lambda j to the 2 lambda j. J goes from 1 to r. And this should also be an integer. Right, and it should be the thing that you normally think of as the conductor of the L function. So we don't know all those. There's a lot of work to be done. But here in this database, a lot of stuff is compiled. Oh, look, there's a Calabi-Yau. What? Uh-huh. So you're saying so Calabi-Yau should be on every single thing there? Is that what you're saying? Uh-huh. Well, so this is, okay, so this table right here is just a sampling to browse. So it's not there's a search capability that I'll show you in a second. But this is, if you just click on degree 2, you get to this page where you can just play around and look at the thing. So this is just a nice little table to just sort of look at stuff and see, a little bit of the variety. But this is just a specially selected table of things to sort of lure you into exploring it more. And the first line is the Riemann hypothesis has been tested pretty extensively. Like all the things in here, there's lots of zeros calculated for these things. And every zero is on the half line. And in some ways, they're all believed, apart from a zero right at the central point, which we know can be multiple, like in the case of elliptic curves, for example, it's believed that all the other zeros are basically transcendental numbers that are completely independent of each other and of everything else that we know in the world. So if that's correct, then you could actually label an L function by its first zero, right? Just the first zero up that you go to, find its first zero, and then just compute that to however many decimal places you need, and that should be a unique identifier for that L function. And so in fact, that's what this column is right here, is the first zero. Here you see the first zero of the Riemann zeta function is 14. This one's all the way up at 17. Okay. Anyway. Yeah. Yeah. I'm sorry? Yeah. Heck operators. Well, so that. Right. Well, so right. So the Heck correspondence only works for small levels, right? In general, for level at most 4, and when you get bigger than 4 in your level, then in fact there's a vector, an uncountably infinite dimensional vector space of solutions. So you need some other information besides the functional equation. But yeah, you're right. No, okay, sorry. But the Euler product comes in and can help you. So yeah, so the belief is that there should be a converse theorem, and that's far, far from proven. The Hecke stuff works for levels up to 4. We have some work that using the Euler product can get you up to around level 19 or something like that by very ad hoc methods, but then after that, it's a great problem. So prove the converse theorem using Euler products, but not twisting in the way that they did. And it should be true. We believe it's true, but we don't know how to prove it. Okay, let's see. What was I going to do? Okay, well, I want to click on this one. So here's this bottom example is the L function of the first rank 4 elliptic curve. So let's click on that. Okay, so there you see. Now, everything's scaled so the functional equation is s goes to 1 minus s. So you don't see the integers in here. I mean, you can see a square root of 2 and a square root of 3 and so on. We're going to put in a feature to allow for an algebraic normalization so that you can see integers here. But the thing I want to show you here is here's the z function of the thing. And it has this really big or small, whatever, this large negative spike here. And it's right basically at the zero, the first zero of the Riemann zeta function, 14.1 whatever. And yeah. You can, did you click on that? So this is on the bottom example. It may still be calculating. Is it still okay? So these pages are made on the fly, actually. So it's had to go to a database, look up the stuff, calculate the z function, and then it doesn't return till it's done the calculation. So maybe if you and I were both doing it at the same time, maybe I was a couple seconds ahead of you. Did it show up yet? Oh. What network are you on? So I'm using EduRoam. Maybe I'm on a faster network. Okay. Well, anyway, so Mike Rubenstein has actually written a paper to explain this phenomenon. And there's an explanation for why you get these spikes at the zeros near the zeros of the zeta function. All right. Okay, let's look at something else. Okay. All right. So obviously I'm biased towards L functions. I'm going to do one more. Sort of degree 3. Now, in degree 3, most of the stuff is really Moss forms. There's symmetric squares of GL2 things, and there's Artin representations of degree 3. But other than that, you kind of, it's not quite so rich. If you click on Moss forms here, this is kind of nice. So these are now for the Moss forms. Now you no longer have algebraic coefficients, and the parameters, the mu's, are presumably transcendental. And so this is kind of an interesting way to display the Moss forms of degree 3, which basically have two independent mu parameters here. And so you just plot them. And each one of these, so you can click on the dots there. And, well, let's see. So it's calculating away. And then this is the L function of that particular Moss form, which had the parameters in the functional equation 18.81i and 8.73i. And then this is just the negative of the sum of those two. Here's the first few zeros, and you can see the z function for that. Okay, now let's see, what else should I show? Okay, well, there's a lot of really cool stuff here. If you look at, so global fields. Let's look at that. Now, if you know what a global field is, then you may be looking for something in particular, in which case you enter the parameters here and do a search. Okay? But if you don't know, then you can browse. So the pages are arranged in a way to have browsing and searching features for everything. Browsing means you never have to take your hand off your mouse, or maybe your finger off your mouse pad, whatever. And you just click around and find stuff. And so if you don't know what you're doing, if you don't know what you're looking for, you don't know what these parameters all mean, well, you can look at the nulls and find out some information. And there's shadowed in things to give you an idea at least of what you might put in. Like you might look, Galois group, well, C5, well, that's probably the cyclic group of 5 elements. And yeah, sure enough, it is. So you can fill some of these things in. These give you suggestions for what to enter. But, global number field. I thought it was on local number fields. Wait, I thought it was on local fields. What happened here? I wanted to do local. Yeah, I want to do local. So browse local fields. And so you've got tables of primes and degrees and the number of different local fields. that satisfy this. Now, see, I know nothing about this, but I find this, I don't know, for some reason, really interesting. Just to be able to browse around here and see. I mean, somehow I learned something by doing this. I learned maybe, the first thing I learned is, oh, for a given prime and a given degree, there's only a finite number of local fields. I did not actually know that before I looked at this page. Anyway, you can click on a polynomial then. So you can go to the, now we're on a polynomial, you can go to the Galois group of that polynomial, and you see all this stuff. So this is, okay, you have to, this is really rich. I mean, there's just a lot of stuff here. And in the current phase of the project, we're really trying to do, over the next 5 years, trying to do as much as we can about degree 4 L functions. The world sort of opens up again when you get to degree 4 L functions. You can have Rankin-Cellburg convolutions of degree 2 things. You can have symmetric cubes of degree 2 things. You can have L functions of hyperelliptic curves. You can have Siegel modular forms, Hilbert modular forms over quadratic fields, Asai L functions. I mean, it just sort of goes on and on. There's 10 or 15 different kinds of things. For the hyperelliptic curves, you have like all the different Sato-Tate groups that go with them that Sutherland and here, so let's look at hyperelliptic curves. Okay, so you can browse, again, by conductor, by discriminant, or you can search if you know what you're searching for. Okay, I don't know what I'm searching for. I'm just going to go by conductor. But say between 500 and 599, there's a label. You can see the equation. Is it GL2 type or not? Well, so GL2 type, I'm not actually sure what that means. Gonzalo, does that mean it's a product of 2 degree 2 things? Or, I mean, your hyperelliptic curve, the L function might be somehow come from GL2, or it might be sort of a genuinely new GL4 thing. Here, let's look at this one. What? Whether the L function factors or not. Yeah, so here's a, okay. All right, so here's the genus 2 curve. Sorry?
So there's a beta on the
Oh, yeah. Oh, yeah, sorry. Yeah, there's a site that... Right, you can do it on your phone, yeah. So I think hyperelliptic curves are only on the beta site and not on the... if you Google LMFDB, you won't find the information about with the... See, there's a beta in the address up there. So you should put the beta in, because then you get more stuff. But it comes without a guarantee. Okay, so let's look at, yeah, so here you see Siegel modular form someday. So that link probably goes nowhere. But eventually it'd be nice if that's connected up with the Siegel modular form. But here, let's go to the L function instead. Now this is a degree 4 thing, so you got really a pile of zeros. So I think this thing is set up to always go between minus 30 and 30. And that's probably going to have to change at some point, because anyway, you can do Artin representations. That also may not be on the, that may only be on the okay, by dimension. So let's, okay, so what does dimension mean anyway? Well, dimension, okay, that's not so helpful. Let's look at 3-dimensional Artin representations. Okay, so we see the polynomials here. So the first one seems to have conductor 229 for a 4th degree polynomial. Here you see the Galois group over here, it's S4, and so on. You can click on, let's do this one, conductor 2 squared times 83. And there's the roots, there's the characters on the conjugacy classes. Here's the L function. So this is computing. Oh, there we go. So this is a degree. This would be a degree 3 L function. Okay. So, all right. Okay. Now I want to show of hands. Who is going to look at this site in the future? I want to see everybody's hand come up. Especially if you're in the front, you have to. Hey, you're not going to look at this site? Oh, okay. All right. Okay. All right. So I actually have some slides also about random matrix theory. And some of this is the same as what John just did. So I don't know if this is good or bad. It's reinforcing or something like that. But there's not much time to go through these slides, right? Because what time do I go to? 11:15? No. 11, okay, I won't go that long. But I don't think I will. But so I put these slides on my website. Okay, so you can, if you want to look at them, you can just download them. So aimath.org/Conrey/IMPA. Okay, so the slides are there. And so I was taking a little bit more. So John shows a very instructive calculation, which I had actually not seen before. So thank you for that, of how to do the pair correlation in the unitary case. And so these slides are a little bit more general and try to look at the different symmetry types that come up in number theory. So in number theory, it seems that the statistics of the L functions we look at are analogous or modeled by the statistics from the classical compact groups with Haar measure, the unitary group, the orthogonal, symplectic. Oops, does this work? Yeah. Okay, so these groups in particular. Now I try to use, I don't know if I stick with this all the way through, but I try to use U in a unitary situation and O in orthogonal and P in symplectic. I don't know if I carry that through entirely successfully, but these are the definitions of the groups. And the eigenvalues are all in the unit circle. In the unitary, they're just wherever. In the other cases, they're symmetric, and the odd orthogonal, you have always one at 1. And these are the Haar measures for these sort of 4 groups. So John showed us this one. And again, this is, as John said, this is when you're working with class functions, so functions that of matrices that only depend on the eigenvalues. Okay, so I like this picture. Just to illustrate the difference between the kinds of statistics you get, or the kinds of spacings you have from a unitary matrix versus Poisson. If you just were throwing darts, and somehow, if you're just throwing darts, well, let's see, you can't really throw darts and land on the circle. So maybe, yeah, you're throwing darts and then project them out? No, that's probably not true either, because it would probably be a different distribution, wouldn't it? Well, okay, somehow or other, you're doing a random number generator, picking numbers randomly from 0 to 1, and then mapping them to the circle. And you can see visually the difference between this. Here you have clumping and big spaces, and here you just have a nice, I would say, a more sort of pleasing distribution in a way. The repulsion, the quadratic repulsion that John talked about means that you can't have too many zeros too close to too many eigenvalues too close together, which I guess in turn means that you can't have too big of gaps. Otherwise, I don't know if that actually follows or not. But and then so here I just took the same number of points as in the last picture. I just started at I took the 96 zeros of zeta starting at 1200 and then just went around the circle. So this would be like 1200. So I just took whatever that interval was and shrunk it down to the length of a circle. So this would be the 0 at 1200, then the next one, and so on like that. And I claim you can see here that this is, it's not Poisson, right? And this experiment, or, you don't have to put them on a circle, just put them on a line segment. This could have been done ages ago. Hazelgrove back in the 40s made tables of the zeros. A lot of people spent time trying to, verify the Riemann hypothesis up to a certain height, but Hazelgrove actually wrote down pretty precisely what all the zeros were. Well, if anybody had just plotted them, they would have realized, maybe, they should have realized, that it was not just random, right? So, so that discovery gets credited to Montgomery or Montgomery and Dyson or whatever. Well, Montgomery gets the credit for realizing that they're not, that there's something different going on. But I claim that could have been done, easily 30 years earlier if anybody had bothered to just plot the zeros. Although I don't know what they would have done. What would they have done if maybe they would have been inspired to try and do a calculation like Montgomery's calculation. By the way, Montgomery's calculation was begun because he was trying to give effective lower bounds for class numbers of imaginary quadratic fields. Okay, so how many imaginary quadratic fields of class number 2, 3, 4, and so on? You need some kind of effective lower bound so that you know when to stop looking. And it turns out that, so that problem, there's the class number formula of Dirichlet, which relates that to the size of the L function of the Dirichlet character associated with that quadratic field. And the critical issue is whether there's a zero very close to 1, a so-called Landau-Siegel zero. Because if there is, then it could make that L value incredibly small, and so you might have a huge D that still had class number 1 or 2 or 3 or something like that. And it turns out that somehow these different L functions kind of know about each other in some sort of perverse way. So as John mentioned in the pair correlation, well, of course, that's still Riemann zeros, but as I showed you with that elliptic curve of rank 4, where you get that spike at the 0 of the zeta function. So there's sort of remnants of some L functions or zeta functions that show up with other ones. And that's the case also with these Siegel zeros. It was known that if there are Siegel zeros, then in fact the zeros of the Riemann zeta function would have to be basically kind of uniformly spaced, or not uniformly spaced, but they would have to be in more or less in, let's say this is the average spacing of zeros of the zeta function. Okay, and then mark the halfway points here. And if there are really bad Landau-Siegel zeros, then the zeros of the zeta function have to appear in basically at one of these marks. And so if you could prove that that doesn't happen all the time, or if at some point, then you would say that you would conclude that there's no Siegel zeros. And so you get an effective lower bound on the class number, and you would solve that problem in a good way. So even right now, the best solution, we believe that the class number h of d of q square root of minus d grows like d to the 1/2 minus epsilon. But the best effective lower bound we have is something like log d, or maybe I think it's just log d. Maybe log squared or log cubed. But anyway, it's not a power of d. And that's based on the Goldfeld-Gross-Zagier work about L functions of rank 3 elliptic curves actually having triple zeros at the center is what they use. So Montgomery wanted to show that, so you could have, so this would be, so you could have your Riemann zeros could be sort of distributed like this, okay? But these would be basically right at the marks, for the average. And so he was trying to prove that didn't happen, so he was investigating the gaps between zeros, and that's what led him to do that pair correlation calculation, and then find out this remarkable thing that led us all off into random matrix theory. Okay, what do I have next? Okay, the Weyl integration formula. So John showed it for the unitary group. Here's what it looks like for SO2n. Vandermon's, John talked about that. And this is a formula that John showed. Let's see. So is this Heine's identity? Is that? No. That's used in Heine's identity. Okay, yeah, right. Okay, and then, right. Now this, I don't know if this came up in your talk or not. But it's a nice, beautiful linear algebra identity about integrating products of determinants. And John motivated the Haar measure. But you can use this, which is pretty simple to prove, and there is a proof in these slides. You can use this to verify that your Haar measures actually have total mass 1. So your constants, the 2 pi to the n factorial, you can get from this. And so, so here it is for unitary. Basically, you want to know, is this equal to 1, right? You just integrate 1 with the Haar measure. So I'm using sort of dun for the Haar measure on n by n unitary group. So that's, so the Haar measure gets written as the square of this Vandermonde, and then if you use that Andreeff's identity, you get this, and then basically this becomes, after you integrate, you only get 1 on the diagonals and 0 elsewhere, and so you get 1. Okay. Now, for our 3 situations, sort of unitary, orthogonal, and symplectic, you want to go through sort of orthogonal polynomials. And in these cases, for these classical groups, it's exactly the Chebyshev polynomials are the ones. So there's sort of 3 different kinds, or maybe more, of Chebyshev polynomials. And these are orthogonal polynomials. And you can use the properties of these. And in general, you can develop sort of a nice part of random matrix theory through families of orthogonal polynomials. Okay. And so the Vandermondes can be written in terms of these orthogonal polynomials. And that leads to new ways to write the Haar measures in terms of determinants with these orthogonal polynomials. And so you can then use, so now before in that previous calculation, we just used what everybody knows about the orthogonality of the exponential functions, but now you can do it with sort of using the orthogonality of the Chebyshev polynomials. Okay, anyway, so you can calculate all these. There's a proof of Andreeff. This is just the determinant of a product. You can take a transpose, which John did in his thing. And anyway, in general, at some point you need to add up the things that appear in here. But if they're orthogonal polynomials, there's this formula Christoffel-Darboux that basically tells you how to add up a sum of sort of consecutive orthogonal polynomials. Anyway, okay, and then, so now, I don't think you mentioned Godin. So if you want to do higher correlations than pair correlations, then the key ingredient seems to be this Dance Lemma. Now, John, you know the history a lot better than I do. I assume that for the higher correlations, this was done by Godin and this method? Okay. And so the key thing is this sort of, sometimes it's called the sort of integrating out lemma. You have, basically, you have big N by big N matrices, and you're trying to do, say, a little n correlation. You want to know what happens with, say, little n of the eigenvalues and how they're all related to each other. And so basically, in your Weyl integration formula, you have integrals with big N integrals. And you want to sort of, you basically get rid of all but little n of them. So you integrate out like one at a time. You integrate out all kind of not extraneous, but you integrate out a whole pile of variables until you wind up with the formula that you're looking for, which is going to be an integral over little n. Okay, little n being the correlation that you're trying to do, or the n-level density. So you have n by n matrices, and you want little n correlation functions, and so you integrate out whatever that means, n by little n variables using Godin's lemma. Now, all this stuff in here is really on the level of of linear algebra and, elementary linear algebra and just calculus of several variables. So this is all completely suitable for an undergraduate class, for example. If you could convince them that it was worth their knowing, or if you thought it was worth their knowing. Anyway, so you basically, f of x theta times f of theta y, if that always integrates to over some interval j to something times f of x y, then if you integrate, do one integral of a big M by big M determinant, you sort of integrate out with these constants here and reduce it to an m minus 1 by m minus 1 determinant. So you keep the determinant structure and integrate one thing at a time. And so anyway, that allows you to, and I'm not going to go through this, that allows you to compute little n correlation and n-level densities. You can take large n limits, and these are the density functions. When you're done integrating out, what do you get in these cases? Well, so this is the determinant that John wrote down. The SU, that's the sine pi theta j minus theta k over pi theta j minus theta k. Okay, and these are the formulas for the other densities. One level density, which comes up a lot, especially in number theory calculations, because basically for any family of L functions, you can sort of almost always do a one level density calculation. For some, if you restrict the support of the Fourier transform of your test function, if you restrict it enough, then you can basically, if you know anything at all about the family and how the orthogonality of the family works, then you can do a one level density calculation. And so you see that a lot. Okay, all right. I think I'm going to stop. I invite you to look at the website and get these slides if they can be useful as a reference, possibly. Thank you.